How do we create intelligence? One logical approach would be to find things in life that are intelligent and try to recreate them. Now, the most intelligent thing that we can identify in life so far is the brain. So to create intelligence, it's probably a good idea to study the brain and design something like the brain, right? Well, that's exactly how we got to the AI models that we know of today, including ChatGPT and image generators like Stable Diffusion and Flux, and video generators like Sora. The backbone behind all the AI we know today is the neural network, and this is based on the design of the human brain. You see, the human brain is essentially a very dense network of neurons. When we receive a stimulus, for example, when we see or smell or touch something new, this information gets broken down into energy which flows through this network of neurons. More on how exactly the brain works in a second, but this essentially is how artificial neural networks work as well. It takes an input, such as a prompt, and this gets broken down into information, otherwise known as tokens, which then flow through the neural network. Think of this neural network as just a series of dials and knobs, and each knob, technically called a node, determines how much information flows through to the next set of nodes. So anyways, this neural network is the foundation of the AI models that we know today. It's just that this configuration is different for each model depending on their use case. For example, GPT would have a different configuration compared with Stable Diffusion, which looks like this. And of course, the number of layers this network would have, plus the number of nodes in each layer, plus the values of each of these knobs would be different too. Now, whenever information flows from one node to the next, a small calculation needs to be made to figure out how much information flows through. Also, during one iteration of training, a small calculation also needs to be made to adjust the values of these dials and knobs. So intuitively, this might not seem like a lot of calculations at first, but let's look at a mid-sized model like the Llama 3 70 billion parameter model. Note that this is just an average model with 70 billion parameters and is less capable compared with GPT-4, which is 1.76 trillion parameters. One round of training for Llama 3 would still require approximately 40 billion calculations, and a large language model usually has to undergo hundreds of thousands of rounds of training. So this just shows you the insane amount of calculations necessary to train these models. Even with the best GPUs and data centers in the world, it takes months to execute so many calculations. Now, as AI models become bigger and more complex, for example, GPT-3 has 175 billion parameters, GPT-4 is estimated to have 1.76 trillion parameters, and you can be sure that the next generation of GPT would have even more parameters. This requires a lot of calculations to not only train the model, but also to use the model for inference afterwards. This is something fundamentally wrong with AI models today. They are very inefficient, and we'll talk more about this in a second. Now, in the world of AI, there is a thing called scaling laws. This describes a phenomenon where the bigger the model, or basically the more parameters you have in the neural network, the more intelligent your model will become, all else being equal. So the y-axis is just the test loss, so the higher this value, the more errors you will get. So ideally, you want this as close to zero as possible. And you can see with more parameters, you'll get a more accurate and a smarter model. So there's a race for companies and nations to build the biggest and smartest AI models, and one way of doing it is to just scale up the size of the neural network or the number of parameters, or also scale up the compute. Now, of course, as these AI models become bigger and bigger, they also become a lot more data and energy intensive, requiring a lot of compute power. The problem is computing hardware that we have today are struggling to keep up with such demand. There has to be a fundamental change in computing, otherwise it's going to be very unsustainable. In other words, you can say that computing is one of the main bottlenecks of us building higher artificial intelligence. So first, let's go over the limitations of current chips for AI computing. and then we'll look at the next generation of chips specialized for AI. Today, the most widely used types of chips in AI are GPUs. As the name implies, GPUs are originally designed for video games and graphics processing. Now, as I mentioned earlier, AI and machine learning often require doing a lot of matrix multiplications through neural networks. Well, it turns out that GPUs, they're actually great at doing this. They work best when doing the same types of operations, such as matrix multiplication, on lots of data at once. This is also called parallel processing. So fast forward to today, most of the tech giants are using NVIDIA's state-of-the-art GPUs such as the H100, and more recently NVIDIA released this Grace Blackwell chip, which is even better than the H100. Now, although these are technically GPUs, so they can also be used in video games and graphics rendering, these are now mainly used for AI. However, there are still several huge limitations of these chips. First of all, they are very energy inefficient. Current chips consume huge amounts of power when training AI models or doing inference. So for instance, training GPT-4 is estimated to take around 41,000 megawatt hours, enough energy to power around 4,000 homes in the USA for an entire year. And the H100, which is currently the most widely used GPU for AI computing, this is notoriously power hungry. It has a thermal design power, or TDP, of up to 700 watts. This is a measure of how much heat a component produces when it's running at full performance. And 700 watts is quite substantial. The human brain, for example, only runs at around 20 watts max. So a single H100 chip is 35 times more power hungry than the human brain. Now imagine a data center of 100,000 H100 GPUs. As you can see here, both Microsoft and Meta have been stockpiling 150,000 of these H100s, and even Amazon and Google are also taking in tens of thousands of these chips. So let's just assume a hypothetical data center of 100,000 of these GPUs. This produces as much heat as roughly 60,000 average homes in the USA. This high power consumption leads to a few problems. Obviously, it leads to huge electricity costs. Plus, it produces a lot of heat and it requires sophisticated cooling systems like liquid cooling. Current computing hardware for AI also leads to environmental concerns due to the carbon footprint of these data centers. Again, going back to the theoretical example of a data center with 100,000 H100 GPUs, this emits the same amount of carbon as roughly 53,000 cars or a medium-sized coal plant. So, to summarize, current computing methods are very power hungry and very inefficient. As we scale up the size of AI models as well as the general usage of AI, current solutions are definitely not sustainable. The second problem of current computing is memory. Even high-end GPUs like the H100 do not have enough memory to run the largest AI models. This is one of the major bottlenecks of AI computing using current chips. GPUs can process data very quickly, but they're limited by how fast they can access data from memory. So for example, the H100 can probably transfer a few terabytes of data per second, which is huge already, but it's still not fast enough for training the state-of-the-art AI models, which are often over 1 trillion parameters. And GPUs don't work alone. They need to get data from the computer's main memory, which is managed by the CPU, and moving data from CPU memory to GPU memory also takes time. This transfer process can introduce latency and slow down performance, especially for tasks that need frequent back and forth communication between CPU and GPU. In contrast, the human brain doesn't have a direct equivalent to memory bandwidth. The brain doesn't contain separate CPU and GPU regions, right? Information processing and storage and memory, it's all integrated throughout this neural network. In other words, information and memory in the brain is distributed across networks of neurons and can be accessed in parallel. So going back to our original intent, if we want to create intelligence by designing something that's like the brain, well, we need to get rid of this CPU and GPU and memory separation that is present in current computing hardware. We need to fundamentally change the design of hardware that's being used right now. You might be wondering why the tech giants are stockpiling over 100,000 of these top GPUs. Note that a single GPU, even the best one out there like the Grace Blackwell chip, is not enough for state-of-the-art models like GPT or Claude, and this leads to scaling issues. We need to link multiple GPUs, often thousands or hundreds of thousands, to actually support these large language models. But linking all this compute together has its own unique challenges. And of course, some efficiency is going to be lost along the way. There are plans to build massive data centers that take hundreds of billions of dollars, but scaling up this compute becomes increasingly challenging and energy intensive. Here's another major problem with current chips. They are very inefficient for sparse computations. Now, what exactly are sparse computations? These are basically computations that involve data with a lot of empty values or a lot of zeros. Many AI models, such as large language models, including GPT and Claude, often work with sparse data. Now, what do I mean by that? For example, when you're chatting with it, it only uses a few words in its response out of all the possible words in the English language. This is an example of sparse data. It's not using the majority of the English vocabulary in its response. However, GPUs are very inefficient at handling sparse operations. GPUs are designed to perform many calculations simultaneously. They work best when doing the same operation with lots of data at once, but the problem with sparse data involving a lot of zeros is that many calculations end up being unnecessary, because you're just multiplying by zero. But the neural networks still perform these calculations anyway, which wastes a ton of time and energy. Now, if you think about it, that's not how our brain works, and that's not how life works. Most of our cognitive tasks involve sparse data. For example, when looking for something in a messy environment, our brain usually focuses on only relevant features while ignoring most of the visual input. In problem solving, only a few key pieces of information are needed to solve a problem, despite having access to a lot of data. The same goes for sensory processing. In fact, most of the time, our brains just filter out most sensory input, focusing on relevant stimuli or new changes in the environment. Otherwise, we would just be way too overwhelmed. In contrast, current GPUs just process everything in the AI model, potentially wasting a lot of time and energy doing unnecessary calculations. This can be a problem if you need to process data quickly and in real time, like for autonomous robots or self-driving. So in simple terms, while GPUs are great at processing lots of data at once, they might not be the best choice for applications that need to do things quickly and in real time. This is a challenge that computer scientists are working on today. In fact, people are actively researching new designs that more resemble how the brain actually works. You see, for neurons in the human brain, when they receive an electric pulse, they don't just immediately fire it off to the next set of neurons. Instead, these electric pulses have to accumulate over time until it reaches a certain threshold, and once it passes this threshold, then the neuron fires a pulse to the next set of neurons, and then it resets back to its resting state. This is called the action potential of the neuron. But this is not how current artificial neural networks work. Once a node receives input, the data is just immediately passed on to the next layer of nodes, but it doesn't really use this action potential mechanism of the human brain. When this type of neural network receives input, all the neurons activate and then fire it to the next layer and then the next layer until it reaches the output layer. All of these nodes are turned on. Plus, it can only process one input at a time, which isn't efficient and much less parallel compared to what the human brain can do. So there's actually a new type of neural network being developed called spiking neural networks. These are designed to include this action potential mechanism. For each neuron in the spiking neural network, it needs to receive enough input to reach a certain threshold before it fires to the next set of neurons. If you want to learn more about spiking neural networks and other promising designs such as liquid neural networks, see this video if you haven't already. But anyways, the reason why I'm mentioning spiking neural networks is because some neuromorphic chips are designed specifically for spiking neural networks. They encode and transmit information as spikes or bursts of activity. and this allows for much higher parallelism and much better efficiency. As you can see here, not all nodes of the neural network are turned on. In fact, most of it remains off until it receives some input. Let me tell you about this awesome tool called ChatLLM by our sponsor Abacus AI. This allows you to use the best AI models out there all in one integrated platform. This includes GPT-4o, Claude Sonnet 3.5, Llama 3.1, and their very own Smog. Not only can you use it like a regular chatbot, but you can also generate images using the best generator out there, Flux Pro. Plus, it has a really cool artifacts feature, so if you're coding or building something with it, it allows you to view and interact with the app side by side. You can also drag and drop PDFs and documents into here for it to analyze. This is great for generating reports and analyzing data easily. You can easily create data tables and charts right in the chat interface, so this is super convenient. They also have a new feature called AI Engineer, which allows you to create your own custom chatbot fine-tuned on your own custom data or instructions. You can seamlessly integrate this into Slack and other enterprise platforms, so it's great for team collaboration. Plus, you can also create custom agents to automate specific tasks. This is just a really powerful and versatile way for you to use the best AI models out there all in one platform. So try it out via the link in the description below. I promise we'll get into the main topic of our video, neuromorphic chips, in a second, but here are some more limitations of current AI and hardware. I really want to emphasize these limitations here because this all relates to why we need a fundamental change in computing and why neuromorphic chips are such an attractive option. So here's yet another limitation. We're approaching a physical limit with current chips. You see, current chips are made of transistors, lots and lots of transistors. These are basically tiny switches that control the flow of electricity, and they're basically building blocks of a computer chip. The smaller these transistors are, the more of them we can fit on a chip, and the faster and more powerful the chip can become. However, we're reaching a point where we can't make these transistors any smaller. So the current size is around 2 nanometers, and that's really small. 1 nanometer is a billionth of a meter. This is a problem because all this time we've just improved computer chips by making transistors smaller and smaller and packing more of them onto the chip, but right now we're almost hitting the size limit. We can't make it any smaller than this. So we'll need to find another way to improve chip performance. So going back to our current goal of creating intelligence, by designing something like the brain, well, here's the current state of AI. We have this neural network, which, yes, it does resemble how the brain works, since the brain is just a network of neurons, but this artificial neural network right now lives in code. It looks something like this. So here you can see we have a neural network. Here we have a layer of 100 nodes. Here's another layer with 100 nodes, followed by another layer, followed by the final layer, which has 10 nodes. So this neural network lives in Python code. And to run this neural network, and to get it to process information, well, we need to use these silicon chips. In other words, a ton of GPUs and CPUs in massive data centers. And this is very power hungry. They produce a lot of carbon and heat and are very inefficient compared with the human brain. So this design doesn't resemble the human brain at all, right? The brain is just one blob which can do all of this. The neural network, the computing, the memory, it's all integrated inside this one blob. So why don't we design something that's closer to this? And this finally brings us to neuromorphic chips. Neuromorphic chips are designed to mimic the structure and function of the human brain even further. Here's a simple explanation of their physical structure. A neuromorphic chip contains a large number of tiny electrical components that act like neurons in the brain. These chips, which we can refer to as artificial neurons, can process and store information. Unlike current computer chips, which have separate parts for processing and memory, as I mentioned before, neuromorphic chips combine data processing and storage in the same physical location, specifically inside each one of these artificial neurons. Each neuron can both process and store information. Now, these artificial neurons are interconnected by these electronic pathways, and this is similar to synapses in the brain, which basically connect neurons together and transmit information between neurons. And in neuromorphic chips, that's what these connections do as well. They allow data to flow between artificial neurons. Now, as the brain learns or forgets things, the strengths of these synapses can also change over time. Well, for neuromorphic chips, as you'll see in a second, the strengths of these connections between neurons can also be adjusted over time. And also, because of this parallel design, many neurons can operate simultaneously and process different pieces of information at the same time. This parallel structure is similar to how the brain works as well. And because we're shifting the neural network from being in code to an actual physical structure, this can have a much lower power consumption compared to current computing hardware. If we use the right materials with the right natural properties, neuromorphic chips can be way more energy efficient for AI tasks compared to current GPUs. So here are some materials that could potentially be used in neuromorphic chips. One popular candidate is transition metal dichalcogenides. These are ultra-thin materials, just a few atoms thick, and they can be used to create tiny switches that use very little power. Think of them as super efficient light switches that barely use any energy when they're off. So these transistors can be used in neuromorphic chips for processing information while spending minimal energy. Another candidate would be quantum materials. These are special materials that have unique properties at the atomic level. They can show sudden changes in behavior, like switching from an insulator to a conductor, and this is useful for mimicking how neurons fire. So imagine a material that can quickly change from being an insulator like rubber to a conductor like metal. If it's a conductor, then it lets energy pass through. If it's an insulator, it won't let energy pass through. And this property is perfect for mimicking the way neurons fire in the brain. This enables the chip to process information very efficiently. Similar to quantum materials, another candidate for neuromorphic chips are correlated materials, including vanadium dioxide. This can also easily change between insulator and conductor states. Again, this property is very useful for mimicking the firing of neurons. Now, it's important to note that neuromorphic chips are still being developed and there's no consensus on the best materials to use or the best configuration for these chips. There are plenty of other materials being studied that could be suitable for neuromorphic chips, including hafnium oxide and lead zirconate titanate, which could be used for memory storage, plus phase-changing materials. Think of this as a material that can freeze and melt rapidly to store information. This is particularly useful for making synapses or connections between the neurons that can change their strength. And this is similar to how learning occurs in the human brain. And perhaps the most well-studied material for neuromorphic chips are memristors. Imagine these as tiny switches that have memory. As you might be able to guess, they're called memristors because they combine the functions of both memory and resistor in a single component. Memristors are typically made of a thin film of metal oxide, such as titanium oxide, sandwiched between two metal pieces. Now, when you apply electricity, tiny particles in the middle layer move around, and this changes the resistance, or basically how easily electricity can flow through this layer. And this change stays even after you turn off the power. So think of it as like a light dimmer that remembers its setting even after you unplug it. Now, in terms of neuromorphic chips, memristors can act like the connections or the synapses between these artificial neurons. They can get stronger or weaker just like how the brain learns and forgets things. And because of their memory feature, they can store and process information in the same place, just like our brains do. This makes them much more energy efficient compared to current GPUs. And unlike regular computer memory, memristors keep their information even when the power is off. This makes them very efficient and suitable for neuromorphic chips. Now, as I said earlier, we're still in the early stages of designing and developing neuromorphic chips. There's no consensus on what's the best design or what's the best materials to use yet, but here are some well-known neuromorphic chips that others have been working on. Perhaps the most well-known and the oldest one is IBM's True North. This chip is one of the pioneering efforts in neuromorphic computing. It's designed to be highly energy efficient and can perform complex computations with a fraction of the power. The chip is made of 4,096 tiny units called neurosynaptic cores. Think of these cores as like mini brains, and these 4,096 cores are arranged in a 64 by 64 grid, kind of like a big checkerboard. And each core actually contains 256 artificial neurons, and they're interconnected with over 65,000 connections. The cores can also communicate with other cores through a special network, and this allows neurons from one core to send information to neurons in other cores. And each core has its own memory that stores information about the neurons. So again, it's integrating processing and memory into the same location, just like how our brain works. Now, information flows through the chip as neural spikes, which are like electric signals in our brains, and this makes it perfect for spiking neural networks, which I mentioned earlier. And unlike regular computer chips, True North doesn't have a central clock controlling everything. Instead, it operates more like the brain, with different parts working independently. This gives it a lot more parallelism, so it's very energy efficient and can process information in parallel, similar to how our brains work. Now, this is just the architecture of one chip, but multiple True North chips can be connected together to create even larger systems, so this is also scalable. Another well-known neuromorphic chip is Intel's Loihi. Here's a simple breakdown of its structure. First, it has 128 neural cores. These are the main parts of the chip that act like tiny brains. Each core can process information independently and is optimized for tasks like AI. It also contains embedded processors which help manage the neural cores and handle tasks like data input and output. And because it has so many neural cores that can operate separately, that means different parts of the chip can work independently without waiting for a central clock, similar to how neurons in the brain communicate. The chip also uses spiking neural networks, which we've covered before. In other words, the neurons in the chip send information through electric spikes, much like how neurons in the human brain send signals. This helps in processing information efficiently and in real time. And much like the IBM True North, Intel's Loihi can also scale easily. Loihi chips can be connected to other Loihi chips to create larger, more powerful systems. This is useful for building complex networks that can handle larger tasks. And because the neural network is now a physical structure, plus because it uses spiking signals, the chip is designed to be very energy efficient, using much less power than traditional computer processors. This makes it ideal for applications that need to process data quickly without consuming a lot of energy. So in summary, this Loihi chip is like a mini brain with 128 neural cores, all working together asynchronously to process information. It's designed to be programmable, scalable, and energy efficient. Yet another well-known neuromorphic chip is the Spinnaker, which stands for Spiking Neural Network Architecture. The architecture consists of several Spinnaker chips. So one chip looks like this, and here you can see 48 of these chips on a board. So again, each chip is like a mini brain with multiple processors working together. These processors do the actual work similar to how neurons in the brain process information. Each processor has its own small and fast memory for data, but there's also a larger shared memory on each chip for storing bigger chunks of information. Each chip also has a router that sends messages between processors and to other chips. It's like a traffic controller for information. And speaking of other chips, as you can see here, each chip can be connected to nearby chips, and this allows them to communicate, kind of like how different parts of your brain are connected. And you can connect multiple chips together like building blocks, so there can be multiple configurations of Spinnaker. Again, this is a very scalable solution. So for example, here we have a board with 4 chips, here we have a board with 48 chips, or the biggest one here has over 1 million processors. And like the other neuromorphic chips, the Spinnaker is great for processing different bits of information in parallel, because each of them can basically act separately. This allows for much greater parallelism compared to current computing methods. It's also optimized for spiking neural networks, so information flows through this architecture in discrete event-based spikes, much like how the brain works. And because of this, it's much more efficient than current GPUs used for AI. Yet another neuromorphic chip is BrainChip's Akida. This is also designed for spiking neural networks, which again is much more efficient in terms of power consumption and is also great at real-time processing. Instead of constantly working, it only processes information when it receives new data, like how our brain only reacts to new sounds or sights. This makes it very energy efficient. The Akida chip can have up to 256 nodes that work together. Again, each node is like a mini brain that can process data by itself, but it can also share information between other nodes, so they're able to communicate in this mesh network. Akida can learn and adapt without needing to connect over the internet. This means that it can get smarter over time just by learning from new data directly on the chip. In other words, the configuration of the chips, such as the strength of its connections or the weights, they can change physically on this chip. Akida is also scalable. In other words, you can connect multiple Akida chips together to handle bigger tasks. Akida is designed for edge AI, meaning it can be used in devices that operate independently from the internet, like cameras, drones, and robots. This improves privacy and reduces the need for constant internet connections. Again, it's important to note that the field of neuromorphic computing is still very new, and people are still trying to figure out what's the best design or configuration or the best materials to use. Several other companies worth mentioning include Prophecy, which develops neuromorphic vision sensors and systems. Their event-based cameras mimic the human eye and visual processing system. So this can be used to process visual data in drones and cameras and robots. This is much more energy efficient and faster compared to traditional methods. Another notable company is SynSense. They are developing an ultra-low neuromorphic processor for edge devices. So again, these chips are designed for sensing applications in areas like IoT, wearables, and smart home devices, and are designed to operate without internet or without connecting to the cloud. Inotera is another company working on neuromorphic processors. Their chips are designed for sensor data processing and AI, and they also aim to use these on battery-powered devices such as smartwatches and smartphones. And again, their chip is based on spiking neural networks, which are event-based and are way more efficient than current neural networks. And another company you might have heard of is Rain AI, which is backed by OpenAI CEO Sam Altman. Rain is developing neuromorphic chips that combine processing and memory in a single architecture, and they aim to significantly reduce power consumption for AI workloads. And perhaps the most interesting one out of the bunch is Cognifiber. They are taking a unique approach by developing fully optical or photonic neuromorphic processors. This means that they're trying to use light for computation, and this can potentially boost speed and energy efficiency by orders of magnitude. I'm sure you know light travels very quickly, so if you use light to power a neuromorphic chip, it's going to be insanely fast. So anyways, that sums up my video on neuromorphic chips. It was quite a long-winded video packed with information, but I tried to give as much background as possible and explain the limitations of current computing systems before jumping into neuromorphic chips. Hopefully this gives you a sense of why we need these chips and what these chips actually do, what they are, and why they might be the future of AI computing. Let me know what you think. Do you think neuromorphic chips are legit? And do you think these will indeed eventually replace current GPUs and power the next generation of AI? And what are your thoughts about spiking neural networks? Do you think this is the path forward, and will this eventually replace current neural networks? Let me know your thoughts in the comments below. As always, I will be on the lookout for the top AI news and tools to share with you. So if you enjoyed this video, remember to like, share, subscribe, and stay tuned for more content. Also, there's just so much happening in the world of AI every week. I can't possibly cover everything on my YouTube channel. So to really stay up to date with all that's going on in AI, be sure to subscribe to my free weekly newsletter. The link to that will be in the description below. Thanks for watching, and I'll see you in the next one.